Yeah, and I also want to thank the organizers for the opportunity to talk here and for putting up this really great workshop. I do realize I'm the only thing standing between you and lunch. I'm also quite hungry, so I'll try to be quick. So yeah, what I want to tell you about today is something that I did a while ago with Jamie Tomaselli, who is a graduate student in Amsterdam. I'm a postdoc there. Okay, so we've already heard a little bit about this yesterday. So suppose tomorrow we detect from some binary merger, we detect gravitational wave signal that has no electromagnetic counterpart. So how do we decide whether that thing is, say, a neutron star or a black hole? And in particular, what role does h bar play in answering this question? Of course, the right answer, as we heard yesterday, is the mass. And this is the usual story. The case of white dwarfs is when you couple fermions to Newtonian gravity, and that's a calculation that was done by Chandrasekhar in 1930, I think. If the density goes up, you reach the point of neutron stars, and then the only difference is that instead of Newtonian gravity, you use GR as the theory, and there's a similar limit called the Tolman-Oppenheimer-Volkow limit in that case. So if the density increases even further, that's typically what people call ultra-compact objects. That's roughly defined as objects such that the radius is smaller than 3 times the mass. But there's an issue with these objects, and classical GR already gives some results that seem to forbid them. There's more, but I'm just mentioning 2. So the first important thing here is Buchdahl's theorem, which puts a bound on the compactness. I'm going to get to this in a second. And the other one is related to the nonlinear gravitational stabilities associated to stable light rings. So what I want to do in this talk is to ask the question of, well, we know how h bar enters in the first 2 points. It was crucial in understanding degenerate stars. I want to understand whether quantum field theory in curved spacetime has anything to say about these last category. So I'm going to start by reviewing these 2 arguments and then introduce quantum field theory and then see what the relation is. So let's start with Buchdahl's theorem. This is an absolute classic. It's a beautiful paper. The statement is very simple. If you take a static spherically symmetric system such that you take a fluid that is isotropic, so all the pressures are equal, and then the metric depends only on 2 radial functions, then if you don't need to, by assuming nothing about the equation of state, and only that the energy density is positive and that is non-increasing outwards, that makes sense because the star should be most compact at the center, and that the Einstein's equation hold, then you can prove that there's a bound on compactness. That means the ratio of R over M. And that's in 4 dimensions given by 9 over 4. So notice that this number is larger than 2 by a finite amount. This means that the Buchdahl, the saturation of this bound, which is known as the Buchdahl limit, is like a finite distance away from the Schwarzschild case, right? So we're not talking about black holes here. So this is usually interpreted as sort of the existence of an absolute bound on the compactness of stars with smooth interiors. So that's one thing. The next sort of no-go result is more recent and has to do with light rings. So the light ring is just the photon sphere, right? That's the region around the object where light can travel in circles. For topological reasons, for solutions that are smooth everywhere in the spacetime, light rings always come in pairs. So how do you find these things? It's very simple. You take the null geodesic equation, you write it in the standard form like this, like kinetic term plus potential equals a constant, and you find the potential. Now, how does that potential look like? That's what I'm plotting here on the left. So if the compactness is, if R is larger than 3 times the mass, then this potential over here has no minimum. Therefore, light cannot travel in circles anywhere in the spacetime. But as you reach R equals 3m, the potential develops a saddle point. And then further, if the compactness is larger than that, so if the radius is below 3m, there are 2 extrema. So there's an exterior light ring that's common also to the one associated to black holes. That's the one that we know most about. It's a maximum of the potential, which means that like photons traveling very close tend to diverge from the light ring. It always sits at exactly at 3M, and it's basically the thing that the Event Horizon Telescope is supposed or should be looking for. Now, what I'm going to talk about today is related to the inner light ring. So there have been some suggestions that if you have an object that possesses a stable inner light ring, then that if you look at the at full GR, that there's some long-lived modes here that will create nonlinear gravitational instabilities. So that's another argument saying that these objects cannot exist in the sense that stars cannot be stable beneath this point. Okay, so one very simple example that exhibits both of these features is a very famous solution found by Schwarzschild. That's the uniform density star. So the equation of state is the density is simply a constant. And again, this is spherically symmetric. Of course, this is an unrealistic solution. We don't expect any star to look like this, but it's a classic textbook solution to the TOV equations. This solution is very important. So these two metric functions have some profile that it's not very important. I'm just showing them here because just to show that they're very simple things. So this solution both saturates the Buchdahl limit, so you can reach the 9/4. And also it has two light rings, the exterior one and the interior one that we're interested in. So I'm going to take this as the background geometry. It's going to be fixed. Of course, you glue it to a vacuum exterior Schwarzschild solution. That's the background. And now we want to study the propagation of waves on this particular background. So there's something really interesting that happens for matter propagating on the geometry of a compact star. Take a massless scalar field, okay, that satisfies this equation, and do the standard decomposition. Go to the tortoise coordinate. We've already heard about that a lot today. And you find an effective Schrödinger-like equation. Of course, the devil is in the potential, right? So here on the left, I'm showing what this potential looks like for different levels of compactness as you get closer and closer to the Buchdahl limit. So this is the exterior. This is the standard vacuum Schwarzschild. We're not interested in that. But these curves are increasingly closer and closer to the Buchdahl limit. So what you immediately realize is that in the interior of the star, there's a sort of well developing that becomes more and more deep as you approach the Buchdahl limit. The other thing that happens exactly in the Buchdahl limit, or the other thing that is happening, is that the range of the tortoise coordinate is extending, becoming larger and larger towards the interior, such that in the Buchdahl limit, the range of the tortoise coordinate goes from -infinity to infinity. That's precisely what happens in the near horizon, well, for the case of a black hole, right? So if you look at this picture, you immediately realize that a potential that looks like this, we already know this from classical and quantum mechanics, this thing is going to host quasi-bound states. And we found the quasi-bound states, we found the spectrum, and that was really nice. You find these super interesting resonances, and we were very happy, Jimmy and I, until we realized that Chandrasekhar had already solved this problem in 92. So that was at the same time disappointing, but it was also gave the feeling that we were kind of on the right track. So if this potential is able to host classical waves, then certainly it can support quantum wave functions. So that was the example for a particular field. So what I want to do now is to jump to quantum field theory and do this from a higher perspective. So how do we do that? Well, quantum field theory, of course, space-time. I don't need to explain you what this means. So the question was whether there exists some sort of generic feature of the stress tensor for these compact objects. One way of addressing this problem is that there's one thing that we know for sure, which is that in even dimensions, the trace of the energy momentum tensor becomes anomalous for quantum field theories. And it takes this particular form in 4 dimensions. The first term is simply the Weyl squared. The second term is the Euler density, the thing that you integrate to get the Euler characteristic of the manifold. And the last term that is allowed is box R. So this is the box of the Ricci scalar. Now the first two terms, their coefficients C and A are completely fixed. We know them for any kind of theory. They satisfy beautiful theorems. These we understand very well. The coefficient of the last term, unfortunately, is scheme dependent, so we cannot fix it. And of course, we don't know of any experiment that could measure this thing. So for now, I'm just going to keep it as an undetermined constant. Now, this is what you can do in general. I'm fixing the reference state here to be the vacuum. However, if in addition, the metric that you're looking at is conformally flat, then all the components of the stress tensor are fixed, not only the trace. I'm just flashing the formula. It doesn't matter what it is. It's well known. Now, it depends only on the coefficients A and D because the Weil tensor vanishes for a conformally flat spacetime. And now it happens to be that the uniform density star, the example that I was telling you about, is conformally flat. There's actually a beautiful theorem by Buchdahl himself about this topic. And he has this remark already 50 years ago that although you can find the solution in all the textbooks, no mention is made of the fact that the interior metric is conformally flat. I didn't know this before working on this project. So since it's conformally flat, all the components of the stress tensor are completely fixed. We know them exactly. So there's no calculation to be done, essentially. Now, there is some relation between what I'm doing here and what people have done here, precisely in Granada. So yeah, this is something we have, there's a lot to discuss there. Okay, so I have the result. What are the properties? So, okay, before showing you the properties, we have this classical fluid. Now we have the quantum field theory stress tensor. How do they compare to each other? So let's look first at the fluid. So I told you that the Buchdahl limit is when R is equal to 9/4 times M. So I'm going to parameterize the distance to the away from the Buchdahl limit with a dimensionless number epsilon, such that when epsilon goes to 0, we hit the Buchdahl limit. So what is the classical fluid doing? Well, I shouldn't call it classical, but the fluid, what is that thing doing? So if you look at the center of the star, of course, in the Buchdahl limit, the Ricci scalar is diverging. And the scale that controls that is precisely the size of the inner light ring. So in the Buchdahl limit, the inner light ring is going to 0, and the size of that thing controls the central curvature. Correspondingly, the pressure at the center is going to infinity, as it should, and the density remains a constant because that's the equation of state we chose. So that's what the classical matter is doing. Now, what is the quantum matter doing? You can just evaluate the formula that I showed you before, and you'll find a very simple object. It is, of course, diagonal, but it's not isotropic, so the pressures are not identical. And I'm plotting this thing here. So in blue, you see the energy density, and in these other colors, you see the two different pressures. So notice they have opposite signs, and they are maximum in magnitude at the center, and then they steeply fall around this dashed line, which is precisely the light ring. And this makes perfect sense because the light ring is the region that is trapping the modes. So they fall by 1 order of magnitude. This is the same, this is the quantum version of the classical trapping that I was showing at the beginning. So as it is to be expected, the quantum terms diverge quadratically faster than their classical counterparts. This is not a surprise, of course. But anyways, this is something you can check. So this is the rough behavior of the quantum matter. Now, there's one thing that if there's one thing you can calculate that gives you an intuition of what's going on, and that's to look at the energy conditions. So the weakest form is, of course, the null energy condition. That's when you contract the stress tensor with an L vector. And for simplicity, just consider a radial vector. So I'm just calculating this thing over here. Now you can prove that, so the classical energy conditions tell you that this object here should not become negative. That's the classical null energy condition. And you can prove that in the Buchdahl limit, the null energy condition changes sign precisely at the light ring. Which again makes perfect sense because the light ring is the region where the quantum fields have most of their support. That's where the waves are being trapped, close to the center of the star. So that gives you a sort of an indication of where do quantum effects become most important. So as a remark here, well, the classical theorems that are used in this field, of course, there are anisotropic generalizations of Buchdahl's theorem, but they require energy conditions. And what I'm telling you now is that energy conditions are violated. The same for the instability associated to the inner light ring. So those theorems, I think there's an interesting interplay because those theorems assumed conditions that now you prove that are violated. So you might want to reconsider them in the quantum field theory. Okay, so the summary is, well, I mentioned a little bit about what you understand by compact objects in GR and some of the no-go theorems that we use to discard them. Then I showed this Schwarzschild interior star just as a very simple background where you can exhibit the features of these no-go theorems, and that is completely solvable. Motivated by the behavior of classical waves in this background, you go to quantum field theory, and then you can do, for this particular case, you can just use theorems and everything is completely solvable. And what you learn is that inside of the star, and in particular inside the inner light ring, the quantum stress tensor, the anomalous stress tensor is growing faster than the background source in the Buchdahl limit, which has nothing to do with the Schwarzschild ray. This is happening way before you form a trap surface or horizon and so on. So that's a region where the quantum back reaction cannot be neglected. Of course, the interesting question is how could you try to make progress in the direction of the back reaction? And I have absolutely no idea. Thank you.
Thank you very much indeed. We have questions.
Mine is short, very short. So, the previous slide.
Yeah.
What do you mean? Maybe I missed something by quantum neck is violated. Can you
Oh,
say?
no, I just mean this.
Okay, so you say that the classical energy condition is violated, but the quantum fluid, right?
Yeah. Maybe I should clarify. All of this stress tensor, all matter in the universe is quantum.
Yes.
So I should probably not use these words. So the distinction between this term and this term is that the first term is the kind of calculation that Chandrasekhar did in the 1930s. You do statistical mechanics for free fermions, and you find degenerate stars. The difference with the second term, and that's the one the first term satisfies the null energy condition.
Mm-hmm.
It's still quantum, but it satisfies the null energy condition. What I'm saying is that if you add the contribution of the anomaly, which you must for fermions and whatever other field you're considering, then the total stress tensor contracted with this thing violates the null energy condition.
Okay. Okay, but the null energy condition is the usual one.
It's the
let's
usual.
say.
Yes,
Okay.
yes.
Thank you.
Thanks for the talk. I think I have to reconcile something in my head. You're saying that if there is a light ring which is stable, then it's believed to be the spacetime is gravitationally unstable.
Yeah.
So I presume but if you relate that to the perturbations to field perturbations, it's because there must be a well as well in the potential for the field perturbations.
Yeah.
But then I suppose I want to reconcile that with the fact that I believe that it's believed that Schwarzschild spacetime is stable under massive field perturbations.
Yes. What do you mean by Schwarzschild spacetime? So the thing is that the kind of solutions that I'm talking about here are solutions that have a regular interior.
Yeah.
The black hole doesn't fall into this category.
Yeah,
in fact, the black hole has only one light ring.
Yeah,
the exterior one.
I know, but the potential for the massive field perturbations do have a well as well. And despite that, there's no instability.
No.
For a massive field.
For a massive field.
it's not a fair question to you because you're not looking at black holes. I suppose I'm just trying to reconcile this in my head.
But if you look at the effective potential in the torus coordinate for the black hole, right? It becomes 0 at infinity.
Yeah.
Then it rises around the light ring.
Yeah.
And then it becomes 0 again.
For massless, yes.
Yes.
But I think
But if you put a mass, the spectrum can only go up.
I thought for massive field perturbations there was a minimum in the potential for the radial potential for the field perturbations. Anyway,
Okay, maybe there's
I
something
think I have to. Just a quick comment. When people look at quantum energy conditions, sometimes people look at average energy
Right,
condition, like
right.
over
Right.
orbit or whatever it is. I don't know if you've looked at it.
Yeah, I mean, I looked into it, but we didn't make any claim because in this particular example, it's not very clear which geodesic you should look at. Yeah.
Okay, we
Thanks.
have a question towards the back and then one in the middle.
Hi, thanks for the talk. The energy momentum tensor, the renormalized one that you found for the partial star, it is anisotropic, right?
It's anisotropic, yeah.
Okay.
So that you can see here that these two pressures are not the same.
Okay, so when you are like compressing it to the Buchdahl limit, you have like two ways of violating the Buchdahl theorem, one because of anisotropies, one because of energy conditions.
Yeah.
So do you have any clue which one dominates?
I expect that the anisotropy is not a big deal.
Okay.
Yeah.
Thank you.
Okay, I think we'll make this our last question.
But it's an interesting. We thought a lot about this. Yeah.
So my question is just a comment. So there's an interesting generalization due to Stutzschlik with a regular with a cosmological constant. So it's Schwarzschild de Sitter was a regular constant density core. Of course, it has a cosmological horizon. So I'm just wondering.
Is it conformally flat?
Well, clearly it will not be, but.
Right.
Yeah. So.
But
it's it's a physically
right,
interesting
right,
generalization.
Right.
Yeah.
Interesting.
Yeah.
Interesting. Okay.